Hey, welcome back to Number Buddy. My name is Buddy. This is episode 2 in our playlist about trigonometry. So we're going to learn what to do instead of memorizing the unit circle. So if you hear the word unit circle and you feel an inner sense of dread, I'm with you. Let's get into it. We're going to learn what to do. So it's not so much that the unit circle contains incorrect information. It's not wrong. It's just that when you memorize the unit circle, you get away from dealing with right triangles as much. And the whole basis of trigonometry is right triangles. So we want to stick to doing everything in the mindset and keeping in mind that really what we're working with is a right triangle. Let's look at what the unit circle is first of all. You may have seen this before. I may have drawn it a little bit different than what you're told. So we're told we have a circle of radius 1. And we want to know what are these XY coordinates of everywhere around the circle, or at least at certain angle increments, at 0, at 30 degrees, at 45 degrees, at 60 degrees. You want to figure out what is the X value of this coordinate here that intersects the unit circle at 30 degrees. So for example, that's this one I've drawn here. What is this X value here and what is the Y value? But there's never really a scenario that you need to know off the top of your head what is the X and Y coordinate for 135 degrees on the unit circle. It's just an artificial situation. Here's what I want you to do instead. So what we're going to do is learn a couple of special right triangles. We're going to draw a special right triangle whose angle above the x-axis is 30 degrees. We learned in the last video, what we're going to do is take the end of that angle, or at least the end of the segment we draw representing that angle, and draw it straight down to the x-axis. Lastly, I'm going to draw in a side here so that we have an x value that represents this horizontal side, a y value represents the vertical side, and then our hypotenuse is going to be z or c. Rather than memorizing the coordinates of an xy point that intersects a circle of radius 1 at an angle of 30 degrees, instead we're just going to learn about the ratios of any 30, 60, 90 triangle. So when we drew this line down here, we formed a right angle there. Because this angle here is 30 degrees above the x-axis, we know this is 60 degrees, okay? We've learned that the hypotenuse is always across from the 90-degree angle. Well, another similar related idea is that the shortest side of your right triangle is always across from the smallest angle. Starting with that side, the ratios of a 30, 60, 90 triangle are always 1 to root 3 to 2. In other words, the side across from your 30-degree angle is what we're going to call our base unit. And whatever that side is, the hypotenuse is always going to be twice that. So say, for example, if this side was 6, okay? If this side was 6, our hypotenuse would have to be twice that. So our hypotenuse would be 12. And our other side, our longer than this side, but still not the hypotenuse side, that is horizontal right now, is going to be 6 times root 3. So whatever that base unit is, which is across from the 30-degree angle, is going to be what you start with. To get the other non-hypotenuse side, you're going to take that and multiply it by the square root of 3. To get the hypotenuse side, you're going to take that shortest side and just double it. This works for any 30, 60, 90 triangle. No matter what you start with, you could start with 100. This side would still be 100 root 3, and this side would still be 200. Okay? So it's the ratio that's helpful, not memorizing the coordinates of the intersection with a radius 1 circle. When we get into actual trig functions like sine, cosine, tangent, and so on, we're going to learn that trig functions are just ratios. Trig functions are representative of ratios. So we always want to be dealing in ratios of sides of right triangles. So let's put this back on there, just in its simplest form. And we're going to say this is 1. This is 1 times root 3. Or you can just write it as root 3. And this is 2. You can write this just as root 3 as long as you remember the reason we got root 3 is we multiplied this shortest side by root 3. It's not just inherently root 3. Okay? Very nice. So let's say instead, what if I gave you this information? What if I said, we're going to start with a z, or a hypotenuse side. We have a 30, 60, 90 triangle, and we have a z that is 22. Okay? Well, the first thing I might do is I might come down here and redraw a 30, 60, 90 triangle, just loosely, right? And I might draw my proportions. I know this is 1, I know this is root 3, I know this is 2. Okay, so if I'm given that z is 22, or my hypotenuse is 22, I know that's twice of what the shortest side is. So if 22 is twice something, that something is 11. So the shortest side is 11. Now I have my base unit, and to get to this other side, this horizontal side right now, we need to take 11 and multiply it by root 3. And we've just solved our right triangle. We could check this if we wanted to into a squared plus b squared equals c squared, right? And this one is 11 root 3 squared plus 11 squared equals what? Let's just say equals what so we can check it. Okay? 11 squared is 121 times square root of 3 squared is just 3. Plus 11 squared is 121. Very nice. 121 times 3 is going to be 363 plus 121. You may have also been able to see that this is just like multiplying 121 times 4. But regardless, we're going to end up with 484. 484 equals c squared. If we come over here and take 22 times 22, 2 times 2 is 4, 2 times 2 is 4, 2 times 2 is 4, 2 times 2 is 4. 484. So 22 squared is 484, and this checks out. So I said this ratio of sides works for any 30, 60, 90 triangle, which means it doesn't just have to be a triangle oriented like this. So we can imagine, what if we took this and flipped it facing this direction? This is still a 30, 60, 90 triangle. My handwriting is all backwards, but we can understand that the same sides are there. This side is 1, this side is root 3, and this side is 2, right? I know this side is 1 because it's across from the smaller angle. But now, if this is a 30 degree above this 180 degree, right? This represents an angle of 150. So rather than memorizing both 30 degrees and 150 degrees, now we can just think of these in terms of ratios. The only difference is, here, because we have a triangle facing this direction, like we said in our first video, this side is going to be negative root 3. Because we're measuring our side as an x value that goes from the origin to that point there, the x value that the side terminates at is negative root 3. Okay? You can check the Pythagorean theorem. Even though it's negative, squaring it will still wind up with the same situation. As a matter of fact, any increment of 30 degrees, with the exception of your 90 degrees and your 180 degrees and so on, with the exception of your axes themselves, what if we said this is a 60 degree angle? Well, we would still draw our line down this way, and we would still make our third side And we would see that our right angle is formed right here. And we would know that if this was 60 degrees, this side was 30. Now the short side, instead of being vertical, the short side is flipped. And the short side is horizontal. And this is our short side, which means this side has a ratio of √3, and this side is 2. So that, in other words, if this, instead of being 1, let's say if this side was 5. This horizontal side was 5. That means our vertical side would be 5√3. And our hypotenuse would be 10. And it works the same way all around the xy plane. Any angle that is an increment of 30 degrees, 30 degrees, 60 degrees, 120 degrees, 150 degrees, 210 degrees. Let's see, 240 degrees, 300 degrees, 330 degrees. These all correspond to special right triangles, 30, 60, 90 triangles, right? We can draw these like that would look like that, or that would look like that. This one would look like this, or that one would look like that, and this one would look like that, and so on. We still have special right triangles. This isn't exactly to scale. Technically, these vertical lines should line up, but we can form these right triangles out of them. The only thing to keep in mind is where your x values and your y values are going to be negative. For instance, if we were talking about this 240 degree angle down here, this would be a 60 degree angle, this would be a 30 degree angle, which means this side would be our short side. Because it's facing in the negative x direction, it would have a ratio of -1. This other side, that's our long side, but not the hypotenuse, would have a ratio of √3, but because it's pointing down, it's going to be -√3. Hypotenuse is always positive. Other sides can be negative or positive, just depending on what direction your special right triangle is facing. Okay, so we've talked about a 30, 60, 90 degree triangle. The other special right triangle to think about is a 45, 45, 90 triangle. Let's look at those. So, from the x-axis, we're going 45 degrees sweeping this way. When we do that, we then take the end of this, draw it straight down, and form our right angle. Okay, we form a right angle there, and now we have two sides here and a hypotenuse. Well, if this angle is 45 degrees, this other angle also has to be 45 degrees, because 45 plus 45 is 90, plus our right angle gives us 180. So if we talked about how in a 30, 60, 90 triangle, the short side is across from the 30 degree angle, and the longer but not hypotenuse side is across from the 60, what happens if both of our angles are the same? And the answer is they are the same. Our ratios of sides, whatever these two sides are, these two sides' ratios are going to be 1 to 1. Whatever this side is also going to be the same. Okay? So when I say 1 to 1, I mean they don't have to be 1. This side could be 10, but that would mean this side also has to be 10. That's a ratio of 1 to 1. So we're going to leave just their ratios up for a moment. When we have 1 to 1, let's see what happens with the hypotenuse, right? We can figure this out with the Pythagorean theorem and say a squared plus b squared equals c squared. Well, if we have 1 squared plus 1 squared, what does that equal? 1 squared is 1. This other 1 squared is also 1. This is just going to be 2. So 2 is going to have to equal our c squared, which means when we take the square root of both sides, c is going to be positive or negative square root of 2. But because we're dealing with hypotenuse, we're only going to take the positive one. So whenever you have a 45, 45, 90 special right triangle, our ratios of our sides are going to be 1 to 1 to square root of 2. And that's these here. These sides always have to be the same, and that's going to make this square root of 2 times that. So for example, if this side was 10, this side would also have to be 10, which would mean the hypotenuse is 10 times the square root of 2. Okay? It's not just the square root of 2, It's whatever your base unit is, which in this case is the same, times that square root of 2. Let's look at what a 45, 45, 90 triangle looks like in a different quadrant. If we go this way, this would have been an angle of 135. An angle of 135 from the x-axis leaves us 45 to get down to the 180 degree mark. So now we have a similar setup, but we're facing this way. So we have 45, we have 90, and if this is 45, we know that's 45. If we want to just keep our simple ratios and say 1 to 1 to root 2, we have 1, 1, root 2. Again, the only difference is, since our triangle is facing this direction, the negative x direction, this side has a negative side ratio. Okay? Same thing works down in this direction. If we have 45 degrees this way, we have a triangle that looks like this. We form our right angle there, right? Our ratios of our sides, we can actually keep this in the same idea here. So this is still a -1 on this side because our x is still facing in the negative direction. The only difference is now our y is facing in the negative direction too. Is this starting to come together? Lastly, let's go ahead and finish this up and look at our fourth quadrant. Remember, these aren't perfectly to scale, but hopefully they can help us understand. So if we had our side ratios here, this is 45 here, this is 45 here, right? The actual angle this corresponds to would be, let's see, 45 degrees short of 360, which would be 315, I think. This is our reference angle. This is the triangle we form. We have ratios of sides of, actually this is a +1 because we're facing this direction, except our y value is negative now. And our hypotenuse is still square root of 2. Those are our main special right triangles, a 30, 60, 90 triangle and a 45, 45, 90 triangle. Now, the last places that exist on a unit circle are the axes themselves. The x-axis and the y-axis sometimes can be a little bit confusing because it doesn't quite seem like a triangle is actually happening there. So, to imagine a 0-degree angle, let's say we started with a 30-degree angle. We'd have a triangle that looks like that, right? But what happens if we were to split that angle in half and go to 15 degrees? Our sides would look like this. Our vertical side would be shortened, and our horizontal side would be about the same. But let's say we split it again and make it even narrower. And now we're getting down here. Well, now our vertical side is getting really short. And as a matter of fact, as we keep going down and down and down, and this angle is getting closer and closer to 0, when we actually get to 0, we have a triangle that's collapsed on itself. Because from the x-axis, we've gone no degrees up. So we're actually right on the x-axis still. Let me make that a little bit thicker so we can see. So our triangle is going like this. It's going this way. It's going 0 amount up or down. And then it's turning back around. Okay? So in that case, the ratio of our sides is we have an x value, a side this way, horizontal value of equal to 1. Our y value is equal to 0, and our hypotenuse value, or a z or c, whatever we want to call it, is also equal to 1. Okay? If we think about 180 degrees, we have a triangle that also is collapsed on itself. The only difference is our x value is -1. our y value is still 0, and our z, our hypotenuse, is still positive 1, because the hypotenuse is always positive, okay? The same idea holds with vertical, except instead of having 0 vertical, we have a vertical that's equal to 1. So now our y value is equal to 1, and our hypotenuse is equal to 1, but our x value that goes this way is equal to 0. And if we go down this way, we have the same idea, except our y value is equal to -1. And our hypotenuse is equal to 1, but our x value is still equal to 0. So those are all the points that are covered by the unit circle. We're using one tool, which is a special right triangle, or we're using two tools. We're using the 30-60-90 triangle, and we're using the 45-45-90 triangle. But whatever angle you're given to work with, you can build your triangle from that. Because as we see when we get to actual trig functions, we want to build triangles every time. Drawing a picture of a right triangle is going to be the most helpful tool you can do. I hope this lesson was helpful for you. Let me know if we need to cover something in more depth. Drop a comment below. Subscribe. Look forward to lesson 3. See you next time. Keep learning.